by itself. So that's why, of course, it wants to leave. For example, if you have an OH group, it's a very poor living group. It doesn't want to leave because it has to exist as OH minus. Okay. So one of the ways we can make it a good living group by protonating it, because then it leaves as a water, which is a very stable molecule. The same thing happens with nitrogen-containing molecules. If we get an N2 as the living group, which is very stable because it leaves as a nitrogen molecule, and therefore it's a good living group. So there is a, we'll talk about more of this later. But you have a living group, and that leaves, and it can leave in two different ways. In the first case that we have shown here, you can do it by using a strong base. A strong base pulls out a proton, this one, so the base therefore pulls out this proton. This then can overlap and kicks out the living group, which is essentially the mechanism of E2 elimination. So you form a carbon-carbon double bond this way, and the base includes a proton attached to it. Now another way the living group can leave, where the nucleophile, which would be this one, attacks directly the carbon to which the living group is attached. So it attacks this and kicks out the living group again. And in that case, we get a nucleophilic reaction, which is essential. So these two are therefore related reactions. And in some cases, they will be competing with each other because you may have something that is both a base and a nucleophile. The alkoxides are similar. They are actually base and good nucleophile, unless they get very linear. One of the ways you can push this reaction one way or other is, let's say you are carrying out the reaction and you want elimination reaction. Therefore, what we do, we use a very bulky base, which cannot approach very easily the carbon to which the living group is attached. So potassium tertiary butoxide is an example. Okay. So this is an excellent base and a poor nucleophile. Why it's a pure nucleophile? Because it's branched. You have three, it's a tertiary carbon. Therefore, it's very crowded and it cannot approach this carbon very easily. And as a result, we get mostly elimination and very little substitution. You can reduce the bulk of that, making it methoxide. So going from this one to, let's say, KOCH, methoxide. So by changing that, what happened now is it's both a good base and a good nucleophile. So it would now make both of these two products. Okay? And the conditions would actually dictate which one will be predominant. And again, we'll discuss that later. So this is essentially a summary of E2 and SN2 reaction. They're kind of related. Going to the other part, you can have the same substrate, but let's assume that you don't provide either a good nucleophile or a good base. Just provide the solvent. So if you have a good enough living group, that's still going to leave, but at a much, much slower rate. And as a result, that is going to cause the living group to leave and generate a carbocation. So this is the intermediate carbocation. And that carbocation can now undergo the elimination, which gives you the same product that we got through the E2, or the nucleophilic reaction where you have a nucleophile. The solvent itself can act as a nucleophile, which is like water, or for example, different alcohols, they can act as a nucleophile. And again, we can manipulate the reaction whichever direction you want to go, but it is less restrictive in terms of making the products than the E2 essential process. But at any rate, they have to form the carbocation as the intermediate. And that's why this is a process where both the base of the nucleophile as well as the substrate are in the red expression. Okay, that's why sorry, only the substrate is in the red expression. So the rate in the later case is K times the substrate, which is the compound with the leading group. So therefore, this is going to SN1 U1 pathway. And the top one is SN2 because the nucleophile on the base is also in the rate expression. That's what we kind of essentially worked out. All right. Any question? Yeah. So the bottom one rate expression is this, and the top one, the rate expression would be rate equals K times the substrate and the nucleophile or base. Both of them appear in the rate expression. All right, so now let's go through the specific reactions that we discussed. And we eliminated all the radical reactions. So we'll exclude that, but all the others that we discussed. How do we make alkyl chlorides, for example? The alkyl chlorides we can make by starting from alcohol. And this is an example. It starts with either a tertiary or secondary. What is shown here is a tertiary alcohol, but it will also work in secondary with a little bit slower rate. But this is really following the SN1 process where we use HCl, which protonates, makes it a better Levy group, and it forms a carbocation. So it goes through the R3C plus H2O plus Cl minus. Now the Cl minus attacks the carbocation and forms the product. So this goes through an SN1 pattern. As I mentioned, tertiary works better than secondary. And when it becomes primary or methyl, then this reaction does not want to form a carbocation, and therefore it changes the mechanism to SN2 process, where the protonated species gets attacked by the Cl minus in order for it to eliminate the water molecule. Okay. And so this changes reaction, it goes to SN2. So these are standard methods of making alkyl chlorides. We can also form from alcohol using thionyl chloride, and this is actually I typed it wrong. So it should be SOCl2, not SO2. The thionyl chloride reaction, again, goes through a process. Let's say this is thionyl chloride. So the ROH attacks the sulfur and kicks out one of the chlorine, forming RO, SOCl plus Cl minus. It's positively charged. In the next step, another molecule of alcohol can remove this proton, or oftentimes we also use a base. A weak base like pyridine is used in order to carry out this reaction. That can remove this proton. So that goes to RO SOCl, and then the Cl minus attacks the R group, giving you RCl, SO2, and HCl. And one of the advantages of using a weak base is this also neutralizes the hydrochloric acid. So this is another method of making the chloride from alcohols. Another way to make alkyl chlorides is from alkenes. And in this case, we add on to the carbon-carbon double bond. So HCl can be added to that. And in this case, it follows Markovnikov's rule, which means that the hydrogen would be added onto the carbon with more hydrogens, which is this carbon. And therefore, hydrogen adds there, generates the carbon cation. And that carbon cation is the more stable one. And then the chlorine can attack this and form the final product. So from alkenes, we can make the alkyl chloride. And essentially the same type of reactions we can also expect with to make bromides, except this one, except this, in which case we use phosphorus tribromide. Rather than thionyl chloride, we use phosphorus tribromide. But these other reactions are very similar for making the bromides. All right? Okay, let's move on to other reactions. Addition of halogens to alkenes. And the halogen addition actually gives you a product which is anti. And in some cases, of course, anti could not make any difference because its rotation is not prohibited. But in this case, like in a cyclic molecule, the bromine should be added on the opposite side. And therefore, if you have to draw the chair form, this is a trans orientation. It would initially probably form the diaxial and then would change to di-equatorial conformance because this is trans orientation. Yes?
You make that remark in the book also that it would often start with the diaxial state. Why is that?
Okay, one of the reasons is like you form, let's say that in the chair form, the structure really is formed like this, the Br plus, that is the intermediate. And now, because both action positions are occupied, it's got an attack from either side, and so it's going to attack from here or here. And therefore, it ends up becoming both axial. And then it flips and goes to the di-equatorial zone. Now, a change of this reaction is that normally this is carried out with, like this is chloroform or carbon tetrachloride, CCl4. And that reaction can be changed by using water, because in that case, rather than the second attack on the bromonium ion will happen from water, and that will end up again still the anti-orientation or trans. Except that one would be bromine, the other one would be OH, rather than two bromines. And one particular thing about this ring opening is the second attack. When you have unequal substituents, as in this case, you have a methyl group. The more substituted ones is where the water attack will take place. Because if you think about breaking the bond from either side, when you break the bond like this one, that gives you a more stable character. As a result, the approach of the water will be from that side, because that carbon will have more positive charge that you can activate. Right? So this is very specific that the OH went to the one with methyl group, and bromine went to the one without the methyl group. But the relationship between the bromine and the OH is trans. So these are essentially the same mechanism by adding the halogen, forming the chloronium or bromonium ion. Chlorine does exactly the same thing. The rates are different, nevertheless they can form the same product. Okay, moving on to the next one, hydration of alkene. The hydration is essentially can be carried out in two different ways. The most easy method to carry it out is use an aqueous acid. Most commonly we use 50% sulfuric acid with water, and that adds on to the carbon again, forming the Marconi capsule, which generates the more stable cation, which is then attacked by the water and makes the alcohol. So it's the reverse reaction of going from alcohol to alkene. Now we're going from alkene to alcohol. And again, as you remember, the La Chatelier's principle applies here in terms of how you can manipulate the reaction. Whether you have want to go from alkene, you need more water, and when you move from alcohol to alkene, then you just take out the water, therefore you use a very dry sulfuric acid. So, now, what if you want an anti-Markovnikov product? In that case, a synthetic method developed by Herbert Brown, who received the Nobel Prize sometimes in the 80s for his contribution to boron chemistry. He developed this method where you use diborane, and it's a two-stage process in which the diborane adds on to the compound, and it adds the hydrogen to the more substituted one. In this case, like this would be the initial product, and you use a solvent such as very high boiling solvent, which is one of the examples is diglycine. In which case, the first product that would be formed is the hydrogen would be added on to this carbon, and as a result, you end up getting a CH2 This is the product that is formed initially, which is then hydrolyzed to form the alcohol. This is the second state is H2O2 in the presence of a base, which hydrolyzes and generates the alcohol. Now this reaction has two criteria to remember. One is the syn addition of H and OH. And the second is that the addition happens in the anti-Markovnikov bubble. As shown in this later case. Okay, the OH must go to this one, and the relationship of this OH and the H are same. They're coming from the same side. Okay. So, any question up to this point? All right, epoxidation. The epoxidation, you don't have to really remember the mechanism. You need a peroxy acid. You can use peroxyacetic acid, peroxybenzoic acid, and a variety of them. So R group is unimportant. Okay, what you need is a COOH. That's what the peroxy acid looks like, and that adds on to the carbon-carbon double bond, changes the pi bond to like sigma bond with an oxygen, forming the three-membered ring system, which is called epoxide. Now, the epoxidation again prefers to go on the carbon that is more substituted. And so this is an example where if I use just only one equivalent of this, then this will not be the product will be this one. Because it prefers to go on the more substituted carbon. And of course, if you use excess, then both of them will be oxidized. And the final reaction that we learned is ozonolysis. In ozonolysis, you use ozone in the first step, which forms an ozonide. And the ozonide is unstable, and typically it's hydrolyzed in the presence of water. But most often we need to add either zinc or dimethyl sulfide as a reducing agent, which essentially, because it generates hydrogen peroxide, in order to destroy the hydrogen peroxide, otherwise it will do further oxidation. And the bottom line is